differentiation. Now, the idea is that y, so we have an expression like this. What you think of is y is a function of x. Okay, so that's the main idea behind doing implicit differentiation. Now let me give you an example of how this works. So what I'm going to do is, or rather, let me explain what the underlying problem is here. So we're supposed to find dy dx, but it's kind of hard to solve this for y. Okay, maybe you can do it with the quadratic equation. Okay, but it's still just kind of weird because you're going to have plus or minus and you have square roots and stuff like that. Also, like with this one right here, this one you really can't solve for y, and right is y equals something function in terms of x. But you can still find the derivative using implicit differentiation, and the way that works is what we're going to do is we're going to take the derivative with respect to x of each side of this equation. Okay, so just take each term and take its derivative with respect to x. So the derivative of this one is 2x. Okay, so that's pretty straightforward. Now this one right here, it's a product. We've got x times y. So minus 10 times the derivative of x with respect to x is 1 times y. So that's the first part of the product rule. And then the second part is the derivative of this y part and with respect to x, and that's just dy dx. Okay, and now here's where it's kind of interesting. When you take the derivative of this as a function, you know, think of y as being, and so maybe rather, you can actually think of, or y is the inner function when you're looking at the chain rule. Okay, so you have y squared, the outer function here. So here, this term right here, inner, think inner is y, and outer, that's x squared. Think that's x squared. Okay, so the derivative is going to be the derivative of the outer function, which is 2x, but evaluated at the inner function, so that becomes 2y, times the derivative of the inner function with respect to x. Okay, so I just used the chain rule right there to differentiate that. And then of course, the other side of the equation, the derivative of 10 is just going to be 0. Okay, and so now what you do is we send these guys to the other side of the equation, and these two terms here, we're going to factor out a dy dx from those two terms. So from these two terms, we factor that out. These go to the other side of the equation. I'll write it as 10y minus 2x. And in the end, I'm going to divide by this to get that to the other side of the equation. And what is this? 2y minus 10x. And that could work, but I guess I could divide everything by 2. So maybe 5y minus x over y minus 5x. Okay, and that should work for your answer right there. So dy dx is this. So now here, the thing is though, instead of dy dx being just completely in terms of x, the trade-off is that it's also in terms of y. Okay, let's take a look at the second exercise. We'll do the same thing here. Okay, so here we have a product. And so when I differentiate with respect to x, I get the derivative of this first part, which is 1 times the second part, plus the first part times the derivative of the second part. Okay, now again, here, with this term right here, the inner is y, and the outer function is e to the x. Okay, so when I take the derivative, I get e to the x times, e to the inner function times the derivative of the inner function with respect to x, which is just dy dx. Okay, then over here, this is 1, and this one is minus dy dx. And then I collect all the terms with dy dx's on this side of the equation. Okay, so this term, I sent that over to the left, and I sent the e to the y to the right. Then I factor out a dy dx. And then I divide by this. Okay, are there any questions at this point about what we've done so far? Just basically, it's just a new technique for situations that otherwise you'd have trouble with.
Sorry, can you explain really quick one more time just how you took the derivative of the right side on question number 2?
The derivative of the right side? Okay. The derivative of x is just 1. And the derivative of y is dy dx. Okay, so remember y as a function of x. So basically it's just, I'm taking each term and I'm taking the derivative with respect to x. And I'm treating y as if it's an inner function or a function of x. Okay.
What does that mean? I remember I remember when we were talking about the chain rule, but I'm trying to remember what does it mean, like the derivative of y with respect to x instead of just like. So I mean, are we taking when we're taking the derivative of x, are we taking the derivative of x with respect to x?
Yeah. Everything is all derivatives are taken with respect to x. So, and if there's any y's in there, the y is treated as if it's just a function of x, an unknown function of x, assuming that you can take its derivative, but that we don't know exactly what that derivative is. Well, we find it out at the end. We find it out in these terms at the end. Okay, so whenever you see a y, then like if the y is displayed as an inner function, like it is here or it is right there. Here this is e to the y. Here this is y squared. Then you use the chain rule. Okay, so the chain rule was used. So this right here, this one right here, taking the derivative of this gave me this piece and that piece. But there's just a y there. That's the easiest one to deal with because it's just dy dx when you take the derivative.
Thank you.
Okay, so let's look at this one right here, number 3. Now, in the next chapter, no, next section, tomorrow, we'll learn how to deal better with this inverse tangent. But what we can do here is, what we're going to do here, what I'm going to do here is I'm just going to, if I take the tangent of both sides of the equation, then tangent of inverse tangent, that's going to just end up with being what's inside. Okay, and then over here, we're going to have tangent of x plus 3x y squared. Okay, so now we do implicit differentiation, and this term right here is product rule, so it's going to give us the derivative of this, which is 8x times that, plus this one, times the derivative of this, which is dy dx. Okay, over here, outer function is, the outermost function is tangent. The derivative of tangent is secant squared. So you would just put that in there. Okay, but then that's going to be multiplied by the derivative of the inside part. Okay, and then derivative of that is 1. Derivative of this is, you're going to use the product rule. So 3. So derivative of 3x is 3 times y squared plus 3x times the derivative of y squared, which is 2y, and then chain rule dy dx. Like that. Okay, so dang, I should have saved a lot more space. Oh well. So now everything, okay, so what I'm going to do is I'm going to go ahead and expand this out. So this is secant squared of x plus 3xy squared. Now I'm gonna split this up into this one plus, and then plus that one. So that's gonna be, this is gonna be 6. But I better keep the same form order. Okay, now essentially this one goes to the left, this one goes to the right. And then I'm going to take this to the left and I'm going to factor dy dx out. I'm going to do 2 things at once. Here, let me do this. Let me put the 6xy out in the front. And I'll put this out in the front too. Minus 8xy. Okay. Then I'm going to divide both sides by this. So I have dy dx. So this goes to the denominator of the other side. And that should work as the answer. If it's not, let me know. Okay, so that's now number 4. Here, instead of y's, we have these f's, and we're supposed to find f prime, but evaluated at 1. Okay, and they give us this extra piece of information. So it's the same thing. This time we're going to treat f as the inner function, and but we're still differentiating with respect to x. So differentiating both sides of the equation with respect to x. Okay, so the derivative of that is going to be f prime. Okay, derivative of this, it's product rule. So we have the derivative of the first one times the second one. Plus the first one times the derivative of the second one. Okay, now here we have f of x to the third. So f of x is the inner function. X cubed is the outer function. So 3x squared is the derivative of the outer function. So you're going to put 3f of x squared. And then by the chain rule, we have multiplying by f prime of x. And then, of course, this one, the derivative of just a constant is 0. That's 0. Okay, now, so we're supposed to find f prime of 1. Now we could group these together. So we could group this term and we could group this term and this term together, and then take this to the other side of the equation, and then factor out an f prime, and then divide by that. Okay, we could do that, but it might be easier just to go ahead and plug in the x equal to 1. Okay, so 1 right here, because that's 1 right there. Okay, and there's 1 right there. So we plug in a 1 everywhere where there's an x, we put a 1. Okay, so that's 1 right there. And then it's f of 1 cubed plus, and then this is a 1 also. And then f of 1, and then f prime of 1. And that's all equal to 0. Now they do say f of 1 is 2. So we're going to do that. So this is, all these become 2's. Those become 2's. Okay, f prime of 1. And so this is 2 plus, and this is going to be 3. That's equal to 0. Okay. So let's see what we got. We got f prime of 1 plus, this is going to be 16. And this is going to be 12. F prime of 1. That's all adds up to 0. Now we can take the 16 to the other side, combine these two. This and this is going to be 13. Take this over there, it becomes a negative 16, and f prime of 1 is negative 16 over 13. Okay, that's a much easier answer to put in than this one, don't you think?
Sorry, where'd you get the 13 from?
The 13?
Oh,
okay,
I see.
So
it's 12 f prime and f prime.
12 and 1, yeah. Okay, so the interesting thing, one interesting thing is when you're doing this implicit differentiation, okay, so we actually have this curve right here, and this doesn't definitively define y as a function of x, because look, it doesn't satisfy the vertical line test. But the thing is, though, this actually does sort of define y as a function of x. I mean, like if we were teaching a different class, then we might be like a lower level class, and we said, no, definitely y is not a function of x in this case. But if you restrict, and say, okay, we're only going to look at this part from here to there, or just like from there to there, then yeah, that y is a function of x. It satisfies and you just like throw everything else out, then yeah, it satisfies the vertical line test. So there we go. And that's kind of how you can look at this problem right here. Okay, so this equation is this weird object right here. Okay, so, and we can use the implicit differentiation to find the derivative to find the slope or the tangent line. So basically we want the derivative at that point right there. And if you plug in a 0 for x, then you do get y being 1/2 as one of the solutions. I mean, you could also get this and this. You get 3 solutions, but 1/2 is one of the solutions. So that's great. Okay, so what you do is you take the derivative of this with respect to x of both sides of the equation. Okay, so this one is going to be 2x. This one is you think of this as the outer function as being x squared, which derivative is 2x, but then you put a y instead of an x, and then multiply by the derivative of the inner function, dy dx. Okay, now here, with this one, we have an outer function of x squared or u squared. That's the outermost function. So we handle that first. So that's 2u, or 2 times all this. And then we multiply by the derivative of the inside. Okay, this one is 10x. This one is going to be 4y dy dx. And then this is minus 1. Okay, so luckily we didn't have to use the product rule there. Okay, so now, what we could do is we could expand this out, but that doesn't sound very fun. So when you start seeing start seeing something like this time, like 3 terms added together to multiply by 3 terms added together, and then at that point you should start thinking, well, maybe there's a better way to do this where I don't have to multiply this all out. And there is, and what it is we're going to plug in that point. Okay, so this is x equals 0, y equals 1/2. So everywhere that you see an x, you're going to replace that with a 0. Okay, and everywhere that you see a y, you're going to replace that with a 1/2. Okay? Okay, so that gets replaced with a 0. This gets replaced with a 1/2. That gets replaced with a 0. Okay, and then here, this is 10. That gets replaced with a 0. This y gets replaced with a 1/2. Dang, we're running out of room here. That's a minus 1 on the end. Okay, so then, so great, that's gone. That's just gone. That's just all 0. This one, it just becomes 2 times a half is just 1. So that's just dy dx. That's gone. That's gone. So we have a 2, and then we have a 2, and then this is 1/4, so that's all divided by 4, and then that's gone, and then this is 2 dy dx minus 1. Okay, so that's all that. Okay, and then so that's basically just 1, so that's just reduced to 1, so that's basically just gone. And so what do we got? We have dy dx equals 2 dy dx minus 1. So let's take that to the other side. So we basically it's dy dx minus 2 dy dx. So that's negative dy dx equals negative 1. And so that means that the slope is 1. So the tangent line is going to look like this. And then that's really nice of them to give us this little picture here. And the slope does look like it's 1. And so the objective is to find the equation of the tangent line. Okay, so we know the slope is 1. So we know that it's going to be of this form. Y equals x plus b. Oh, and this is the y-intercept. 1/2 is the y-intercept. So it's going to be y equals x plus 1/2 is the answer. Okay, because the y-intercept is 1/2. Okay, great. Any questions on that? Okay, let's go on to the next exercise. Here we're supposed to find the second derivative. The second derivative. Okay, so let me show you how to do that, how that's done. So here's what we do. let's go ahead and take the derivative of respect to x, like we're finding the first derivative, okay? So this first term gives you y. Okay, the derivative of with respect to x is 1 times y plus x times dy dx. Okay, that's the first term. The second term is 2e to the y dy dx. Okay, now this is a little confusing, but it's just a constant, so that's derivative is 0. Okay. Oh, I didn't realize there's just other information right here at the point where x equals 0. Okay, so if x equals, so let's do this. Let's work it this way. This has to be done. This part had to be done anyways. So let's work it this way though, for a second. If we take this equation and we set x equal to 0, we get 2e to the y equals 2e. Well, 2e is the same as e to the 1, right? So that means that y equals 1. Okay, so now we have x equals 0 and y equals 1. That's going to come in handy later. So one thing that I want to tell you guys to be careful about is when you have values for x and y, you plug those in after taking any derivatives, and not before. Don't plug it in before taking a derivative. Plug it in after taking derivatives, because if you do it before, then you're just going to get nonsense. Okay, so
but the reason we do that now is just to get the y value.
Yeah, because that'll come in handy later. That'll come in handy later. But that's not, we're not. So what I'm going to do, I'm going to do two things with this. Okay. First thing is I'm going to take the derivative again. Okay. That's the first thing I'm going to do. Second thing I'm going to do is I'm going to solve for this. I'm going to solve for dy dx. Okay. So the first thing I'm going to take the derivative again. Okay. So this piece is this is dy dx. This piece is product rule, so that's the derivative of the first part, which is 1 times the second part, plus the first times the derivative of the second part. So derivative of this is the second derivative. Okay, and remember, that's what we're after. Right there, I guess I could have used, yeah, this is the second derivative. I guess I could use this notation. I should have used that notation. Oh well. Then the derivative of this piece. So that's the derivative of the first part, which is 2e to the y dy times the second part. So I'm gonna end up with 2 of these plus 2e to the y times the derivative of this part, which is the second derivative. Okay, so I'm just going to get down to that point. Okay, now over here, I'm going to solve for dy dx. I'm going to factor dy dx out of that right there. Okay, so the y I took out to the other side. I factored the x plus 2e to the y, or I factored the dy dx out of these two terms, and then divide by this. Okay, now I'm going to plug in 0, 1. So x is 0, y is 1. So I plug a 1 in there. X is 0. That x is 0. and then a 1 right there. Okay, so that's negative 1 over 2e is what I get for dy dx. Okay, oh, I forgot there equals 0 here for this in this equation. Okay, now what you can do, now the objective is to find the second derivative. Okay, to find now our objective is what I'm going to do here now is plug in, okay, x equals 0, y equals 1, and dy dx equals this, negative 1 over 2e. Plug all those in, okay? So this becomes negative 1 over 2e. I guess I could have combined those first.
I just have a quick question. When you did the second derivative, when you derived it again, just for the 2e to the y times dy dx squared, how did you get the dy dx squared?
How did I get this right here?
Uh-huh. Yeah.
Okay, so the derivative of the first part, the derivative of e to the y is e to the y times dy dx. But since I already have a dy dx, that's going to be 2 of them, so squared. So it's the product rule. So this term right here, this term, this gives me that one and that one by the product rule. So this first one is the derivative of this times that. The second one is this times the derivative of that. Okay,
Yeah,
so, oh, this is great. Yeah?
That's the only reason why I'm confused of why it's squared, because wouldn't it just be 2e to the y times the, like, which is the derivative, and then times the dy dx plus the derivative of the 2e to the y times the derivative of dy dx, which.
Wait, what?
Let's see. Okay, so for example, with that term that's x times dy dx, when we took the derivative of that, we did the derivative of x became 1 times dy dx plus x times the derivative of dy dx, right? So, but the dy dx, the x that became 1 and the dy dx didn't become squared there. So why is it squared for the second part when you're taking the derivative of 2e to the y times dy dx?
Why is this squared?
Yeah.
Okay, so this piece right here, when you take the derivative of that, use the product rule. So it's the derivative of the first part times, that's the derivative of this. The derivative of this is this.
Okay, so the
Times
dy dx is included. Oh, right, because the.
So the derivative of this is right here,
Mm-hmm.
and then times this that's already there.
Okay.
Okay.
I see. Okay. Thank you.
Sure. Okay, so now we're plugging everything in, and this is really great because x is 0, so yay, that just goes away. So that's just 0, yay. Okay, now this one, whoa. This one is going to be, okay, y was 1, so that's going to be 2e, so y is 1. And then you have dy dx squared, so that's this right here. That's squared. Okay, and then this piece right here, y is 1 again, so that's 2e. And then the second derivative, now I should have used this different notation because they kind of like wrote it that way. So this also represents the second derivative. It's the same as this. Okay, so this becomes negative 1 over e. Those two combine. And this is what is this? What? Something's wrong. Oh yeah, this is 1 over 2e. Yeah, what the? Oh my goodness. One over 2e. Okay. All this is 1 over 2e. Those two combine to be, or I guess, you know, maybe I should have just left them. This would be easier if I just left it apart, if I just left these separate. So I want there just to be no confusion. That's that and that. So those will cancel, right? This goes to the other side of the equation. And now I divide by that, and we have y double prime equals 1 over 4 e squared. So that would be the answer. 1 over 4